Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the awesome stuff. This is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Valentina Di Marco with us today. Hello, Valentina.
Hi, Frank. How are you? Thank you for having me today.
Oh, well, thank you for agreeing to talk about your very lovely article. And it is my November 7th here in Phoenix as we record this, but I think you are somewhere else. Where are you located at?
Yes, I am in Australia. I am now in Geelong, but I am usually in Melbourne. So Geelong is the south of Australia, and it's fairly sunny and nice today.
Beautiful, beautiful. Awesome. You like plants. You have some great
I
growing
do.
plants all over the
I
right.
love plants a lot. And my supervisor too. We all love plants. In the office, we have plants. Yes. You
Beautiful.
nailed it straight away.
Very cool. Very, very cool. And Valentina, what do you like to do for research?
Okay, so I am a PhD student in Monash University.
When you
And
graduate?
my research focuses on I work on PTAs, pulsar timing arrays, and gravitational wave detections. My interest is on anything that is gravitational waves, really. But my background is in statistics because I have an MPhil in statistics, and so I like to look at the statistical aspect of astrophysics.
Cool.
So
Very cool. And when do you graduate?
when will I?
No,
When did I graduate?
when do you graduate PhD?
Oh, I am a PhD student. I am an MPhil. I did an MPhil in statistics, which I finished a year and a half ago.
Okay.
And so now I'm in my second year of my PhD.
Got it. Got it. Well, I look forward to calling you Dr. Di Marco at some point. So that'll be very cool.
Me too.
That'd be very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. Toward robust detections of nanohertz gravitational waves. And Valentina, take us away.
Thank you. Okay, so this paper really, again, focuses on statistics. It focuses on the way we use some of the statistical tools to make a detection of gravitational wave with pulsar timing experiments.
Cool.
These are gravitational waves that are different from the gravitational wave that LIGO, Kagra, and Virgo detects.
Mm-hmm.
These are due to supermassive black holes and perhaps even other physical phenomenon, but we focus on supermassive black holes. And they are nanohertz gravitational waves. They are in the nanohertz frequency band. These are very difficult to detect because they are very faint, and this is a gravitational wave background as opposed to one event.
Bang, right.
Yeah, so for us, this is like detecting noise in noise, which is very complex.
Indeed. But fun.
So what we do is that we use many statistical tools, different statistical tools to assess the detection. And one of the tools that we are using are these quasi-independent scrambles.
Okay.
Now, it's important to notice that these are not the only statistical tools that the collaboration use to make a detection. They use Bayes factors, for example, as well. And, every collaboration uses different methodologies. But these are one of the tools that we use. One other important thing to notice is that recently the collaboration have been coming out with the first detection of gravitational waves. Now, first of all, I would like to thank my collaborators and my supervisor that have been working on this paper with me. Cool. You, Zeke, and Eric Train and Ryan Shannon are my supervisor. Eric Train being my main supervisor, and Matt Miles and Daniel Reardon as well have been helping in the production of this paper and the creation of this work.
Cool.
And we are part of the pulsar timing collaboration, and we work together on also the detection. So
Nice.
And going back to the detection, this paper comes at the same time as when the pulsar timing experiments have been officially coming out with the first detection of a gravitational wave background. So it's exciting times.
They're very definitely. Indeed. Okay.
So how things are done and where things starts. The pulsar timing arrays are very many. There are very many collaborations around the world that have been working together for the past many years, sometimes in the excess of 20 years, but surely more than 10 years, in collecting data in order to make this detection of this nanohertz gravitational wave background.
Mm-hmm.
So the collaborations are important to cite here because we have been working together tirelessly to do all this and make this detection. So the EPTA is the European Pulsar Timing Array, and the Indian PTAs have been working together in their paper. The Nanograph collaboration, this is the North American Observatory, Nanohertz Observatory in America. And then we have the Parkes Pulsar Timing, which uses the Parkes telescope here in Australia.
Yes.
These all form the International Pulsar Timing Array, which is a consortium of consortium. This is also been, this work has been done also in collaboration with other PTAs, including the Chinese pulsar timing and MeerTime that uses Meerkat in South Africa.
Yes.
So it is a lot of work, and it is a very exciting time to be here because of these detections.
Yes.
It is therefore even more important now than any time before to be sure that the statistical tools that we use are exactly what we think they are, and that they are as accurate as we think they are.
Cool.
And this paper focuses, as I was saying, on specifically one type of statistics, which is an optimal statistics.
Okay.
Now, what we are searching for, we are hunting for something here. As I was saying, this is noise buried in noise, and we can't just look at one pulsar and assess the presence of a gravitational wave doing that. Instead, what we do is that we look at the cross correlations between the signals coming from pulsars. Yes. And if there is a gravitational wave washing over the pulsar and Earth, then we expect to see the cross correlation to follow the Hellingston and Downs curve. And this Hellingston and Downs curve, the actual function of it, it's here on equation 1. It looks like this, simple as enough. The important thing to take away from this equation is that it only depends for pulsar timing on the angle of separation between pulsar pairs.
Yes.
And I would like to scroll down a second now and have a look at what it looks like, because this is our baby, and everybody is very much interested in trying to find this specific curve in our data.
All right. Figure 6.
Figure 6 at the start of the appendix, yes. So there you go. So this is the purple line that you see in this plot. On the horizontal line, this is the angle of separation, as I was saying. And you see that this curve has a almost quadrupolar shape. And here we have a simulation of some data, the dots with the error bars, and you can see that they do follow quite well this Hellingston down. But we will go back at this later on. This is though what we are hunting for, this shape, the cross correlation between pulsars.
Yes. Okay. Very cool. Let's go back up to our equation for Hellingsdowns. Equation 1. Oh, there we go.
Yes. Yes. So this is what we're looking for. And so if we can scroll on page 2.
Sure.
Okay. So as I was mentioning, recently the collaboration have made some detection, not quite 5 sigma detection yet, but very close, and we are all very excited. And we can see that every collaboration have been working on their noise analysis differently and got somehow different results. There is a summary of these results over here. But ultimately what we are all doing here is trying to find this Hellingston Downs curve. And
Right.
what we do is that we look at the signal and we assess the noise. We want to assess what the noise coming from pulsar it looks like. That's the first thing we need to do. And this is very complicated. The reason why we want to do that is because when we have the data coming in, we can calculate p-values looking at the distribution of the noise only that we could have.
Okay.
But as the noise analysis is super complicated, it's really, really difficult because this is not an instrument on Earth. This is basically a giant experiment in the sky. And pulsar can be affected by very many sources of noise, like dispersion measure, like difference in rotation, so many things, and chromatic noise. All these noise are white or red, and gravitational waves is also red noise. So if we don't assess the noise, if you don't do the noise analysis precisely, then we could have either misspecifications of the noise, and this can lead to false detection or underestimation of our detections.
Right.
So it's important to know this noise very well.
Indeed.
However, we can't switch off gravitational waves. We don't have to switch and say, hey, let's have a look at the noise.
That would be nice.
That would be nice, but can't be done. So what we do instead is that we scramble and shift things around, and I'll explain better what I mean here, in order to destroy the signal in our data, the gravitational wave signal in our data, and be left with something else that is only noise.
Okay.
This way we can calculate the p-value and assess the reliability of our detections.
Okay.
Now, here in this paper, we only look at the optimal statistics as a statistics to calculate these p-values.
Okay.
Sometimes I refer to as the cross-correlation optimal statistic or cross-correlation signal-to-noise ratio. It's the same thing all the time, but it's just one of the statistics that are used. And Sky Scramble are used when we assess how this statistics is the noise of this the noise only due to this sorry, the statistics to only to noise. I can say that today.
Yeah, you can get you got it out.
Too much sun. Anyway, this is what we're looking at. These optimal statistics. Now, if we go to section 2, I won't give away what this is all about. I just keep going and explain how we do things. Now, if there is a gravitational wave, this is, here on page 2, keep staying up because we need to look at this equation number 3.
Okay.
This is the definition of the optimal signal-to-noise ratio. And it is important now at this stage to look at it, because in this definition, first of all, it will be used later. But this is really the statistics and all it looks like. And in the denominator, you will see these two quantities, Pi and Pj's, which are the power spectral density of the noise only. And this is important to know. So the cross correlation is calculated, this optimal signal to noise ratio is calculated using, taking into account this, the noise, the power noise for each pulsar. And then there is this quantity Q, which is the optimal filter, which it's in equation 4 down there. And this is in a nutshell what we use. The optimal filter Q contains the quantity gamma ij, which is the Hellingston and down curve. Right? Basically, each and every one of these gamma ij are the Hellingston and Downs parameters. This is exactly where we are in that curve, basically, for that angle of separation.
Okay, F is frequency.
Cool. So this is our player. This is our main player, right, Frank? This is what we look at. So if we go down now.
Question. Oh, here it is. Okay, S is the spectral power density. Okay.
Yes.
Gotcha.
Yes, correct. S is the spectral power density. We can write the two things this way. Basically, yes, define that omega over F3.
Okay, I'm with you. I'm with you. Okay, I'm up with you to equation 5. I'm good. Okay.
Cool. So now, if the stop there.
Okay.
Thanks.
Sorry. Bandwidth lags.
This is very important because
It's all good.
okay, so if the signal to noise ratio is well specified and there is no signal is in the noise,
Okay.
in this in our signal, there is no gravitational wave in the signal, then the cross correlation, this quantity rho, is supposed to follow a generalized chi-square distribution. So we know the shape of that distribution.
Okay.
And this has been a recent paper from Jeff Hasbun, which was really interesting to see. But if we, on the other hand, have a misspecification of the noise, then the distribution of rho is not anymore the generalized chi-square.
Yeah.
And so it might completely change shape or width.
Okay.
So it's important to notice that.
Yeah. Mm-hmm.
So quasi-resampling method like sky scramble and phase shifts have been used already in astro a lot, and specifically they are used in the LVK or LIGO-Virgo-Kagra collaboration, the interferometer on Earth, in the form of time slides. And they do that to understand if there are glitches in their detectors. So again, they want to assess the noise, the same thing that we want to do. So they take two detectors and they cross-correlate their. They shift one of the detector data of a certain amount, and then they cross-correlate. And what happened then is that if there is a signal that is common to the two, it will remain. It will be destroyed. Okay. And therefore, we are left with only the glitches due to the single machine. So it's something that we use, and we already know how it works.
Okay. Okay.
And now we in poster timing use two of these methodologies interchangeably, and we look at them because it's important to be sure that we're doing the right thing. One, the sky scramble takes the sky and scramble the position of the pulsars. So it gives them a new home in the sky. We find we uniformly find them a new location. And this way, we clearly change their angle of separation. Yes. And when we do that, because the helix and downs depend on the angle of separation, we destroy the signal in the data, the gravitational signal in the data, and we're left with only noise, at least in the way we have formulated this problem so far. Yep. And phase shift, though, something different in the sense that it's the phase that is shifted. And when we do so, we also destroy the signal in the noise, but we create a new signal altogether. Yes. And this way, we shift vertically, basically, those cross-correlation. And what happened is that, again, we have the effect of destroying that Hellings's and Downs curve in the data, maintaining the noise that is left down. So these are our tools. These are the tools that we use. And we want to understand how reliable these tools are and how they work and how they are used by the collaboration currently. Mm-hmm. So if we scroll down a second, I would like to show you I'm taking it mine as well here.
All good.
Yes, so we know that these scrambles and shifts have though an issue. We know that they saturate at some point. And what really saturation means is that at some point we can't find more independent scrambles, but they will be dependent from, they will just not giving us more data and information once we add them. Okay. Saturation is a problem for every scramble, every resampling method. And the amount of, we need to assess how and when our scrambles are independent. And to do so, we use a match statistics. This match statistics is in equation 12 over here, as you can see. This M, this quantity M over here, is what the collaboration are using currently as a match statistics to assess this independence. Okay. And it only depends on the Hellings's and Downs parameters, those quantity gammas that you see over there.
Yep.
These quantity gammas are gamma ij, where I and j are two different pulsars, while the prime and unprime define the different skies. So we take a sky, a new scramble, and we compare it with the old scramble or the original sky, and we get a match statistics.
Yes.
If the skies are identical, the match statistics will be equal to 1. If, on the other hand, these two skies are completely independent, then this match statistics will be 0.
Oh, okay.
There is a caveat here. If we want to only use 0 and completely independent scrambles, we will be able to generate only a very small number of independent skies.
Okay.
And because the p-values that we can generate with the skies is dependent on the number of independent scrambles we can get, that means that we cannot calculate p-values that are very high. So if the formula here is that the p-value that we can generate is 1 over, it's smaller than 1 over the number of independent scrambles. That equation over there, yes.
Yes, that one. Right.
So if I only have 10 scrambles, then the p-values cannot be very precise. We just cannot go very high.
Right.
So,
okay, I'm with you.
So what can we do? The collaboration knows that, okay, independence is good. We can take quasi-independent as well. It means that we take numbers that are close to 0. And that's okay, because, I mean, 0.1 as a threshold is a small threshold. And that's why we call this method quasi-independent, because they're not quite independent. They are quasi-independent. So far, the collaboration, at the time this paper was written, we're using a threshold of 0.1. And here we will be using exactly that threshold. Everything that is calculated from now on is with a match statistics with a threshold of 0.1.
Okay. All right.
So here's basically the point of the paper is in this section 3 over here. What we do in this paper is to first assess the common definition, the definition of this match statistics that has been used here by the collaboration. And this is point 1 on this section here. It looks like the definition that the collaboration are using so far, it's not suitable, at least at the time, it's not suitable for a real pulsar timing array. Because the real pulsar timing array has differences in the way the pulsars are timed. The quality of the pulsars is important here, and it has not been taken in consideration in that equation 12 that I showed you up there. As you remember, that equation 12, just up there, takes only in consideration the cross correlation, the Hellingston-Down parameters.
Right.
And that's it. So there is nothing to tell us anything about the power of the noise here or how well the pulsars are timed.
Okay.
The second, so we introduce here in this paper a new definition of the match statistics that do take in consideration. Now, this has been done before. It's just that we have calculated this from first principles, and we have defined also then, or this is in point 3, a new match statistics that takes into consideration both sky scramble and phase shifts. And the reason why we want to do that is because this way we can generate a higher number of independent scrambles.
Yes.
And then also in point 2, we point out that so far the collaboration have been using a threshold only for sky scrambles and not for phase shifts. And we argue that if this is an issue for every resampling method, it will be an issue also for phase scrambles.
Indeed.
So these are the 3 points that we make on this paper and following from here. And this is in equation, the following equation that we'll see here in page 4. We'll show you how basically number 16 here, the number 15 and 16.
You're gonna weight it. Okay.
Yeah.
You're weighting it.
Exactly. So what we do is that we introduce weights. These weights take in consideration here in equation 17, the power spectrum of the noise, as
Right.
well as the quantity omega over F6. And so the reason why we define the match statistics this way is because we take the ensemble average, we define the statistic as the ensemble average between the signal to noise ratio, our statistics,
Yes.
in two skies. And so we define it that way, and if we plug in basically the quantity of rho that we've seen above, then we get this equation 15 and 16.
Cool. Yep.
This weight will come back again later on, so bear with me. And this is the new definition for the sky scramble. This is the new definition of the match statistic for the sky scramble. This definition will have consequences, and we'll show you in a little while. But in the meantime, we'll have actually quite strong effects on the number of independent scramble that we can generate.
Indeed. Also, yes. I'm with you.
So now the fact that we have weights here, it's kind of an intuitive thing. And what does this really mean is, imagine you have 100 pulsars, and you only have a couple of pulsars that are very, very well timed, and all the other are timed okay, but not, just a little bit not as well as the other two. Okay. Then the number of effective pulsar in our array gets reduced dramatically to a number closer to 2 than close to 100. Okay. And that means that suddenly our network of 100 pulsars, it's much smaller. And because what we can detect really depends on the number of pulsars that we have in our array, this affects our ability of make a calculation of the p-value. Indeed. But this is not a judgment of the quality of the network in the pulsar network. This is more a comparison between the network. So if you have good pulsars, well-timed, and then you add one that is super well-timed, okay, that will mess up things for you more than if you had, some kind of all equally timed pulsars.
Okay. A good one is worth its weight in gold.
It's having those very 2, 3, 4, whatever, strongly well-timed pulsar kind of affects this a lot.
Yes.
Okay. Now, as I was saying, we also introduced a match statistics for sky scramble, which wasn't done before, and we use the same definition as we did for phase shifts. This is, again, the match statistics is the ensemble average of the two signal-to-noise ratio, or the statistics, that quantity in brackets over here.
Yes.
And so if we scroll down a little bit, we see the new expression for the match statistic in equation 18 over here.
Okay.
This takes into consideration the phases. And again, you have this quantity pi and pj and omega squared over f to the 6th. And again, this is different from before. The derivation of all this, by the way, it's in the appendix. We'll talk about that later in a little while.
Yes.
And then after this, we define our very own super scrambles, because, again, we wanted to have as high a number of independent scramble as possible. Yep. We thought, well, we could mix the two things together, and so the sky scramble and the phase shifts, and create this super scramble and this new match statistics that, again, takes into consideration the relative quality of the pulsars in this equation 19. Yes. It looks scary, but really, if you call that omega square f6 py pj, I don't know, omega, as OW, whatever, that it is quite simple what it does, right? We have these weights again appearing over here. And let's have a look now at the consequences of these. And I would like to jump directly down to the pictures that everybody likes, the pretty pictures.
Pretty picture figure one.
The pretty pictures.
Let's do global on figure 1, which is on the left column here.
Yeah. So these plots show you saturation. On the horizontal line, you have the number of proposed scrambles. So every time that we generate a scramble, we propose it, and then we calculate the match statistics. The scramble, this match statistic is done between the new scramble sky, all the previously found new skies, and the original sky. So each time we have to add an operation to all our operations done before. We check against everything else done before.
Okay.
And we can accept it if the match statistics is below that threshold,
Yes.
or reject it. On the vertical line here on this plot, you can see the number of accepted sky. So if it gets harder and harder as long as we go to find new independent skies. This is intuitive. And what we see here is that we do at some stage saturate. Now, these two plots at the top don't quite saturate yet. But we estimate that we would have been reaching saturation at around 1,600 scramble. Something to notice here is that these first three plots are done with the match statistics, which was originally used by the collaboration. The one does not take in consideration the difference between the pulsars. So in a normal regime, we know that we reach a certain number of around, for example, for nanograv, around 1,600 new skies or new scrambles. Definitely not enough to go up to a 5 sigma detection with a threshold of 0.1. This is important to notice.
Yes.
For EPTA, for the European collaboration, again, we probably would have reached around 800 or 900. And for PPTA, even less. With that, because we have a lower number of pulsars in our array, in PTAs, we would have reached around 150, maybe 160. So this is the situation as of now.
Okay. Good.
But if we instead use the new match statistics, the number of independent skies that we can generate is dramatically reduced. And in fact, figure 2, I show the sky scramble. Now, this is the saturation plot for sky scramble only. And I put the 3 collaboration all in one plot. In this dashed dot line in blue for the European collaboration, and then nanograv in orange dashed line, and the PPA in purple. Again, remember that the number of independent sky will depend on how uniform the quality of the pulsars are in the array. No, it's not a definition of quality of the overall array. It looks that with this new definition of match statistic for sky scramble, we really don't reach more than 30 independent scrambles. So we can't do much with this, right? It looks like a little bit of doom and gloom, but there is light at the end of the tunnel, don't worry.
Oh, yay, hooray. It's not heading in the right direction here yet.
On the other hand, in figure 3, we can see the same plot, but for sky scramble, for phase shifts with the new definition of match statistics, again with the threshold of 0.1. And again, sky scramble perform a bit better than phase shifts perform a bit better than sky scramble, but just marginally. It's as if we cannot reach more than 70 or 80 independent skies.
Right. Okay.
So
we're a long
the
way.
sky scramble maybe perform better. Maybe we get a little bit more with sky scramble. After all, that's the reason why we introduced that. And that's the following figure 4, which show the saturation for the super scramble.
Super scrambles. Okay, both of them. Okay, and much better.
And again, yes, we see
Order
again. Yes, we can increase things quite substantially. That is good because also we can save time. One thing to notice here that I didn't clarify very well is that you can see that these plots are not quite saturating yet. Here for PPTA, you see that we are not quite plateauing yet, right? The reason is that it takes a long time to run this scramble. Every time they generate a new sky, we have to check against everything else before.
Right.
And so, and it gets harder and harder to
Sounds
get
like an n-squared problem.
So, so this is basically because we didn't want to spend weeks doing this, that wasn't the purpose of this paper. We got our code to break after 2 hours of not accepting a new sky. So if we tried for 2 hours and it wasn't accepting new skies, that was just for us to know that, after 1 week, that's where we are now, fine.
Okay, I'm good.
So again, even with this super scramble, we still don't reach enough independent skies. However, this is the important bit. This is not all doom and gloom. First of all, we did question, why do we need a threshold? Can we remove completely the threshold? What happens if we take
lower, change it, just change it.
Completely dependent scrambles? Yes, I mean, the thing that we know for sure is that if we take dependent scrambles, completely dependent scrambles, then we cannot generate, we are not looking at the distribution of the noise anymore. We're looking at something else.
Correct.
This is not just a null hypothesis anymore. So what are we looking at? Can we use this? Can we use this for hypothesis testing? And the answer for us is yes, we think we can. Cool. And we'll see that the collaboration because we have been in touch and talking to the collaborations about this all the time while the papers where we've written, and it looks like, in fact, we can remove that threshold. At least we can increase that threshold, and they have proven that the p-values, they get, doesn't change much if they go from 0.1 to say 2 in the threshold.
Okay.
So if we can, so here basically in the next in the next section 5.2 and 5.3, we kind of give a toy example, or actually 2 toy examples on when things can go right and when things can go wrong.
Go south. Okay.
So these are only toy examples. They are just for illustrative purposes.
I understand.
But here we take first in consideration correlated scrambles, no threshold, but with sound assumptions. And in here, the toy model is composed is only 2 pulsars,
right?
And with 1 just frequency. So the signal here, the gravitational signal H, the strain here, it's only a complex number. In here, A1 and A2 are the amplitudes, and then the phases are the phi1 and phi2.
Yes.
Now, with only 2 pulsars designed this way, all we can do is to estimate 1 raw, and this is 1 statistics.
Yes.
But we can define a detection statistics X, that is the cosine between the 2 phases, the difference between the 2 phases. If there is a Huntington down signal in our data, then the 2, the H1 and H2 will tend to be in phase. And if this is the case, then our X statistics will tend to 1. But if there is no signal, now we expect the 2 phis to be uncorrelated and X will be 0. Okay,
I'm with you.
Then we can scramble things and we can build a new distribution using X. The new distribution for raw is using X, and calculation p-value here, basically.
Sure, okay.
We calculate the p-value using these X statistics, and what we notice here is that the p-values that we generate here are correct, in the sense that if a p-value of 0.001 will be seen 0.1% of the time. So it does what a p-value should do. That's basically the point.
Good.
Then we go ahead and we scratch our head and we're like, oh, can we break the game? Can we make things go wrong? And we then created a new different model that has unsound assumptions, in the sense that we assume the noise from the pulsar to be not really realistic. Pulsar noise is not like this. But what it is for us is, in this example, a step function with random rise and random sign. So, and each step will have the same amplitude. So it's basically a random step up and down. And again, this is not real. This is not really the noise from pulsars. But what we wanted to achieve here is to see what happened when we choose. When the phases of different frequency beams are correlated, and this violates the implicit assumption of phase scrambling. And what happened here is that, in fact, we do end up generating p-values. Then we go ahead and we do the same things. We calculate the cross correlation statistics. We calculate the p-values, etc. And what you can see is that when we do this with this noise, then we will get a underestimation of the p-value. You can see that in figure 5. And so in red on this figure, you see the p-values that we obtain with this depth function. And in blue, we compare that with the Gaussian noise, which is what the correct one, the one that we know have reliable p-values.
Okay.
And you can see that the p-values are very much underestimated. And again, this is a toy examples, and there will be room to study this better later on. But it was just for us to kind of tell, hey, things can go wrong. Can we now make can there be things in the noise that look like this? That's a question for later. But for now, we see that things could, in principle, go wrong.
Yes. Good.
So we had other solutions to this as well, though. So we can remove the threshold, or we can at least increase that threshold from 0.1 to something a bit higher. And the collaboration has seen that, yes, actually this works with real data. And this is very important, right? This is the reason why we wrote the paper, so we could check things.
Right.
Another solution for us would be, and this is here in this equation 23, is, okay, well, we have a match statistic that does not take in consideration at all the difference between the pulsars. And then we have our new match statistics that takes in consideration everything. Could we tweak things around so that we trade off signal to noise, and we consider a suboptimal signal to noise while we make our calculation? So we could, for example, introduce this new filter function, this quantity QI. If you remember, that's in the definition overall.
Yes.
And this has this quantity beta here that will control the shape of the filter that we put in. So if beta is 0, that is equivalent to treat each measurement the same way as we have seen in the old mesh statistics used by the collaboration.
Right.
And while the beta equal to 1 would correspond to our new definition of match statistics. And we can have this as a dial going as big and as small as we want to achieve what we need, trading, as I was saying, signal to noise. Finally, we also have we have been thinking about this for a while. We're not really sure if this is a solution that is better than what we are already using. But we could use instead a new statistic that is a coherence statistics that completely ignore the amplitude of the residuals of our signal altogether. So we only take the steps, we only take the sign basically here, that EYIJ over module of YIJ here.
Yeah.
And this is again similar to something that has been proposed before. The problem with this is that we are not sure if this is actually more robust than what the sky scramble and phase shifts are. So there is more study, there is more that has to be done to assess this. There are options and things that we can explore maybe in the future. But the most important thing that came out of this paper is that maybe we can remove or at least increase this threshold and still have valuable p-value that we could use for our detection. And so, yes, as I was saying, we can keep going to the things that we're doing, just increasing that threshold. There is an epilogue here. There is an epilogue because by the time we wrote the paper, then the collaboration were coming up with this detection, and a lot of work have been done by the collaborations and other people to assess these things.
Yes.
We know for a fact that we are going to make even stronger detections very soon. The collaboration will keep working and they keep collecting data. No, we don't know if, as a fact that is going to happen tomorrow. We don't know, but we know that we're working towards that. And because we're working towards that, eventually we will get to a point where we have this 5 sigma. Removing that threshold or increasing that threshold will allow us to get there faster and better. So this is what have been done now. We have some, we're still looking at the data from our collaborations, and we point out that different collaborations have different results.
Yes.
The powerful things is that a collaboration are working together in this IPTA, this consortium of consortia, to iron out all these things, which is very exciting. Very cool. And moreover, there is a paper, the same paper that I mentioned before from Jeff Aspun, that shows that the distribution that we see is actually consistent with the theoretical distribution expected for the noise model.
Oh, okay.
So this is a very good point. This is here on this, just down here on the next paragraph here.
Next paragraph. Did I miss that?
So yes, this is where we are at. We are now in the process of working more on this. So yeah, stay tuned. This is all coming together in
soon.
One thing that I wanted to, before I leave this, I wanted to show you something on this. If you scroll down again on the first image that I showed, the picture on down the appendix. Not this one, the one with the Huntington Downs curve in the appendix.
Yes, we're just bandwidth.
Here you go.
Just
there you go.
Yeah.
This is a simulation that was done with no gravitational wave. And so this was the starting point of our all concern so what was happening, it's not surprising that we do get some random situation in which we do see a Huntington down. The worrying part was that we were seeing this a lot more often than expected.
Yes.
And this is with like no signal whatsoever. So that was what started everything. So yeah, so the optimal statistics here, there were no detection, and it was happening 10 times more than what it was supposed to happen, or something. Like I can't remember now exactly the numbers, but it was happening quite often. So that's it. As I was saying, in the appendix down here, you can find all the derivation of everything. The data is also available on GitHub if anybody's interested.
Yay.
The derivations are, it looks scary, but really they are just plugging in one thing into the other, and
it's still awesome looking. It's still awesome looking.
Thanks. Thank you.
I think this is really great, and figure 5 is the money shot so far. So very good. Very, very cool. Figure 5. Nice. Valentina, thank you so much for walking us through your very awesome APJ paper.
Thanks.
Yeah. And you mentioned it a couple of times, leading hints, let's call them. But so let me push on a little bit and ask, where do you think we go with this over let's say the next 2 to 5 years? It's a rapidly moving field. So I don't want to say a decade, because I think things will move a little quicker than that. But yeah, where do you think we head from here, given what we got? Maybe there's already more data in the pipeline, etc.
Yes, so our collaboration keep looking, and more data is collected continuously, and we are putting together the existing data already in the IPTA data. So this will put together the nanograph, the Indian PTA, the European PTA, PPTA here in Australia, all together into one giant data set that will allow us to, with the data existing already, be more sensitive to gravitational waves. So we'll see something better. There are the Chinese and the maritime collaboration that have super precise, new, huge radio telescope that will allow us to get there in a shorter time that it took to the other collaborations to get there, perhaps because of the precision of the tools that they have. So this is an exciting time, and I cannot make a prediction of when, but it is it is possible that in the next decade we'll get something, I would say even less, but I guess, right? But it's all in the workings, everything is being done. From my very personal point of view, because I'm interested in the statistics, I am now currently working on breaking the game again for these optimal statistics and the match statistics, because I am that kind of person. So what I'm trying to do is, okay, we have seen that there is this noise that is in this toy model that is not really realistic, and we can see that things can go wrong.
Yeah.
The question that I was asking was, okay, can we break the game again, but with realistic noise? Right. Are there instances where we can generate a kind of a step function in our residuals that mimic that behavior? And the answer is yes. Jumps exist in our data. Jumps are due to change in tension, for example, in the telescope, and they cause our residuals to jump up and down. So these are instrumental issues, and usually we can see them. Jumps are important jumps. You can see your residual going whoop, and you eliminate that, right? Because you know the jump is there. Right. However, we might have micro jumps that are, for example, in the order of 400 nanoseconds, or like small jumps that they're not detectable in our residuals, and they can still give us a situation similar to what we see in that toy example. Hint is that so far, but I'm not 100% sure about this right now, is that we have an effect on our p-values, but it's in the other direction. It looks like we are safer even. So that's actually quite good. But again, until we have final data, we can't say much, but this is what I'm working on now. Similarly, I'm working on any other form of misspecification. I'm very much interested in every form of misspecification that can affect our abilities to make a detection. And so anybody else out there that is interested in misspecification, please let me know, and I'd like to have a chat and learn more and maybe collaborate on something.
Cool. Go check out that GitHub page. Very cool. Very nice. Valentina, thank you so much. That was really good. And that will do, everyone. Yep, that will do, everyone. And hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.